A psychology professor once wrote to the Hayden Planetarium asking permission to study why visitors left our space show clinically depressed. His specialty, apparently, was factors that make people feel insignificant, and he wanted to administer questionnaires measuring the psychological damage we had done to their sense of self-worth. But here's what that Ivy League professor missed, and what most people fundamentally misunderstand about cosmic scale. The problem is not that the universe makes you small. The problem is that you walked in with the wrong ego, and your intuition about cosmic distances is not slightly off, but off by a factor of 7. A miscalculation so severe, it changes everything about what it means to exist. Most people believe the universe spans about 13.8 billion light years, because light has been traveling for 13.8 billion years, and that reasoning feels completely logical until you learn it is completely wrong. The observable universe, just the part we can see, stretches 93 billion light years across. Not 13.8 billion, not 27 billion, which would be twice that age, 93 billion light years, and that is only what we can observe, while the actual universe could be infinite. Human brains evolved on the African savanna to track predators, find ripe fruit, and remember which tribe members could be trusted. Nothing in 4 million years of hominid evolution prepared us for the reality that space itself can expand, that the fabric of existence can stretch, while everything embedded in it goes along for the ride. We are curious primates using 3 pounds of electrochemical tissue to decode mysteries operating on scales our ancestors could not have imagined. And the fact that we have succeeded at all is the remarkable part, not our occasional confusion. Understanding the common error comes first. When people hear the universe is 13.8 billion years old, their brains perform simple arithmetic. Light travels at roughly 186,000 miles per second, making that the cosmic speed limit. No experiment ever conducted has detected anything with mass reaching that speed. So, if light has been traveling since the beginning of time itself, the farthest we could possibly see should be 13.8 billion light years in any direction. Double that for diameter, and you get a universe about 27 or 28 billion light years across. Sounds reasonable. That reasoning would be correct if we lived in a static, unchanging cosmos, the kind of universe that even Albert Einstein originally imagined. Einstein introduced a mathematical term into his field equations of general relativity, the cosmological constant, specifically to prevent the universe from expanding or contracting. He wanted a static, eternal cosmos because that matched the philosophical assumptions of his era. He later called that constant his greatest blunder, but the cosmos does not care what Einstein wanted. A Belgian priest and physicist named Georges Lemaitre proposed in 1927 that the universe might be expanding, that all of space might have originated from what he called a primeval atom, a single point from which everything emerged. The scientific establishment largely ignored him until Edwin Hubble changed everything 2 years later at Mount Wilson Observatory with the most powerful telescope of his era. Hubble discovered that galaxies were not moving randomly through space, some toward us and some away. Distant galaxies were not moving slower than nearby ones. What Hubble found was that nearly every galaxy in his sample was receding from us, and the farther away a galaxy sat, the faster it appeared to flee. The universe was not static but expanding, and Lemaitre had been right all along. This is where most people's intuition collapses. When we say the universe is expanding, people picture an explosion with matter flying outward through space, like shrapnel from a bomb. That is not what is happening. The Big Bang was not an explosion in space, but an expansion of space itself. The fabric of the cosmos is getting larger, while everything embedded in that fabric gets carried along. Picture a photograph being printed on a balloon. As you inflate the balloon, every ink dot moves away from every other ink dot, Not because the dots are crawling across the rubber, but because the rubber itself is stretching. A dot that started 1 centimeter from your dot ends up 2 centimeters away. A dot that started 10 centimeters away ends up 20 centimeters away. The more distant dots appear to be receding faster, even though nothing is actually moving through the rubber at all. The rubber is simply stretching everywhere at once. Now imagine that balloon is infinite in extent. The dots are galaxies containing hundreds of billions of stars each, and someone keeps inflating it faster every second. That accelerating inflation is what we call dark energy, and I will return to it because it represents the largest component of the universe, about which we are almost entirely ignorant. Our universe works the same way as that balloon, with every galaxy thinking it occupies the center of the expansion, because every other galaxy is moving away from it. There is no center, or rather everywhere is the center, because your intuition wants there to be a cosmic ground zero, some location where the Big Bang happened, but the Big Bang happened everywhere simultaneously. All of space was once condensed into that primordial state, and all of space has been expanding ever since. One of the most profound aspects of cosmology deserves emphasis here. There is no center of the universe, no edge you could travel to and look back at where it all began. Every point in space has equal claim to being the location of the Big Bang, because the Big Bang was the expansion of space itself rather than an explosion within space. Galaxies are the ink dots, space is the balloon surface, and the dots that are far enough away appear to be receding faster than the speed of light. Not because they are moving through space faster than light, which would violate relativity, but because there is so much space between us and them, and all of it is stretching at the same time. Everything in the known universe was contained about 13.8 billion years ago, according to precision measurements from the European Space Agency's Planck satellite mission, in a volume less than 1/trillionth the size of a pinpoint, packed into a space smaller than a subatomic particle. Temperatures reached 10 to the 32nd power degrees Kelvin, so extreme that the laws of physics, as we understand them, break down completely, putting us in the realm of speculative physics, where no experiment can yet guide us. What we do know is that the universe began expanding from that state, and as it expanded, it cooled in the same way that compressed gas heats up and expanding gas cools down. As the universe cooled, different physical phenomena became possible. Subatomic particles formed first, then atomic nuclei. Within the first few minutes, in a process called Big Bang nucleosynthesis that produced mostly hydrogen and helium, the two lightest elements, before about 380,000 years after the beginning, the universe was opaque. Free electrons scattered photons in every direction, like trying to see through plasma fog. Once electrons combined with nuclei to form neutral atoms, photons could suddenly travel freely, and the universe became transparent. The light released at that moment is still traveling through space today. In 1964, two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to eliminate persistent static from a horn antenna they were using for satellite communication experiments. They thought pigeons were nesting in the equipment. They cleaned out the bird droppings, cooled the receiver, pointed the antenna at empty sky, and the static remained. That static turned out to be the cosmic microwave background, the oldest light we can detect, the afterglow of creation itself, showing us the universe as it was when it was just 380,000 years old. Penzias and Wilson had stumbled onto the birth cry of the cosmos while hunting for pigeon excrement. They won the Nobel Prize in physics. That light has been traveling toward us for 13.8 billion years while space kept expanding the entire time. And this is the piece that makes the mathematics work out to 93 billion light years. Light left distant regions 13.8 billion years ago when those regions were much closer to us. That light has been traveling toward us ever since. But while the light was traveling, space kept expanding, and the matter that emitted that light kept getting farther away. By the time the light reaches our telescopes, The stuff that emitted it now sits about 46 billion light years distant, rather than 13.8 billion. Double that for the diameter of our observable sphere, and you get roughly 93 billion light years. What theoretical physicist Alan Guth at MIT calls cosmic inflation helps explain why this expansion was so dramatic. In the tiniest fraction of a second after the Big Bang, space underwent exponential expansion, doubling in size again and again, faster than anything we observe today. This inflationary period, proposed by Guth in 1980, solved multiple problems in cosmology simultaneously and stretched the universe far beyond what the simple age times light speed calculation would suggest. And here is where it gets stranger. Those distant galaxies whose ancient light we are just now receiving currently sit 46 billion light years away and are still receding, moving so fast that the light they are emitting right now will never reach us. Space between us is expanding faster than light can traverse it. We will never see what those galaxies look like today. We will never know what civilizations might have risen and fallen in those distant cosmic neighborhoods. They are leaving our observable universe forever. This thought haunts me as an astrophysicist, a recurring nightmare about what we might be missing. Distant galaxies now visible will ultimately disappear beyond an unreachable horizon, carried away faster than light can travel, a feat allowed not because they are moving through space at superluminal speeds, but because space itself is carrying them away. In 1 trillion years, anyone alive in our local group of galaxies may know nothing of other galaxies at all. Their observable universe will merely comprise nearby gravitationally bound stars, while beyond this island of light will lie an endless void. Future astronomers will have less evidence than we do. The cosmic drama that we can still observe, barely, will have been carried beyond their detection. Unless contemporary astrophysicists across the galaxy keep exceptional records and bury an extraordinary trillion-year time capsule, future scientists will be denied access to key pages from the cosmic story. They will not know galaxies ever existed beyond their own because the evidence will be gone. That realization torments me. The question of what cosmic evidence has already been lost to us, what truths were obvious to hypothetical observers billions of years ago that we will never recover because the evidence has already receded beyond our horizon forever. Numbers help anchor the abstract. The observable universe contains approximately 2 trillion galaxies, according to recent estimates, revised upward from the 100 billion we counted before. Deeper surveys revealed the small, faint ones we had missed. Each of those galaxies contains, on average, somewhere between 100 million and 100 billion stars. Do the multiplication, and you get something like 10 to the 24th power stars in the observable universe, a number called a septillion in American nomenclature, more stars than all the grains of sand on all the beaches of Earth, more stars than all the sounds and words ever uttered by all humans who have ever lived, a quantity so vast it dwarfs anything you have conceived of in daily existence. Those 2 trillion galaxies, with their collective septillion stars, are not the universe, but just the part we can see. The observable universe is like your view from a boat in the middle of the ocean where you can see to the horizon in every direction and sit at the center of a circle of visibility, but just because you cannot see beyond that horizon does not mean there is nothing there. We sit at the center of our own observable bubble, but an alien civilization on a planet 40 billion light years away has their own cosmic horizon, sees their own 93 billion light year sphere, sits at its center too. Their observable universe overlaps with ours in some regions while extending into regions we will never access. The whole universe, not just what we can observe, remains unknown in its full extent. It could be twice as large as what we see, or 1 trillion times larger. And current evidence from the Planck satellite data on the cosmic microwave background's geometry suggests it might extend forever in all directions, without end, spatially infinite. The piece we can see, as staggeringly large as it is, might be an infinitesimally small fraction of the whole, making us residents of a cosmic speck looking out at a cosmic speck in what might be an infinite ocean of cosmic specks. Something happens when people truly absorb this information. I have seen it countless times in lecture halls and planetarium shows. Something shifts in their eyes. Some find it exhilarating, and some find it terrifying. And the difference often comes down to whether they walked in feeling cosmically entitled or cosmically curious. The Hayden Planetarium's Space Show Passport to the Universe takes visitors on a virtual journey from the streets of New York City to the edge of the observable cosmos. Earth shrinks to a dot, the solar system shrinks to nothingness, and the 100 billion stars of the Milky Way become a barely visible smudge on the dome before that too vanishes among billions of other galaxy smudges. Within a month of opening day came that letter from the psychology professor wanting to study our visitors' depression. Every time I experience that cosmic zoom, I feel alive and spirited and connected. I feel large, not small, because the goings-on within this 3-pound human brain are what enabled us to figure out our place in the universe. People who feel diminished when confronted with cosmic scales walked in with the wrong expectations. If you entered believing you were large and important and central in some absolute cosmic sense, then the universe is going to correct you. But if you walk in with no such pretension, recognizing yourself as a participant in something vastly larger than yourself, then the grandeur of the cosmos does not diminish you but elevates you. Your body is a forensic record of cosmic violence. A detective examining your atoms would find evidence from at least 3 different crime scenes. Hydrogen, forged in the Big Bang itself 13 billion years ago. Carbon and oxygen manufactured in the cores of massive stars that died before our sun existed. And heavy elements like gold created in the collision of neutron stars or the explosive deaths of the most massive suns in the galaxy. You are walking evidence of stellar catastrophe. And the chain of custody for your atoms stretches back to the first moments of existence. The details matter here, because this is not poetry, but measured physical fact. Stars generate energy through nuclear fusion, slamming small nuclei together to make bigger ones. Our sun fuses hydrogen into helium right now, having done so for about 4.6 billion years, with another 5 billion to go. But our sun lacks sufficient mass to create heavier elements. It will end its days as a white dwarf, a cooling ember of carbon and oxygen, never having manufactured the nitrogen in your DNA or the iron in your blood. High-mass stars make those stars at least 8 times more massive than the Sun. These stellar giants burn through their hydrogen faster, and when they exhaust it, they fuse helium into carbon. When helium runs out, they fuse carbon into oxygen, then oxygen into neon, neon into magnesium, magnesium into silicon. Layer by layer, these stars build progressively heavier elements in their cores, like an onion made of atomic diversity. Iron stops the process because iron has the most tightly bound nucleus. You cannot extract energy by fusing iron into heavier elements, the same way you cannot power an engine by rolling a ball from the bottom of a valley. Once a massive star develops an iron core, its fusion furnace shuts down, and without the outward pressure of fusion to support the weight of the overlying layers, catastrophe follows. In a fraction of a second, the core collapses. The outer layers come crashing down, then rebound off the dense core in an explosion we call a supernova. That explosive, instant-lasting mere seconds releases more energy than our sun will produce in its entire 10 billion year lifetime. In that cataclysm, elements heavier than iron are forged through rapid neutron capture processes. The gold in jewelry, the silver in surgical instruments, the uranium in reactors, all created in the death throes of massive stars or the mergers of neutron star remnants. Astronomer Vera Rubin, whose observations of galaxy rotation curves provided some of the first compelling evidence for dark matter, helped establish that these heavy elements spread through galaxies in predictable ways that reveal the underlying gravitational structure. These supernova scattered ingredients became part of gas clouds that condensed to form the next generation of solar systems, stars with orbiting planets that now had the raw materials for rocky worlds and liquid water and complex chemistry. When I look up at the night sky and know that we are part of this universe and that this universe is in us, what matters most is the second part. The cosmos is not merely something we inhabit, but something that constitutes us. We are not metaphorically but literally made of stellar material, biologically connected to every living thing on Earth through shared biochemistry, chemically connected to all molecules through common atomic origins, and atomically connected to all matter in the observable universe through our shared emergence from the Big Bang. A single molecule of your DNA contains roughly as many atoms as there are stars in a typical galaxy. We are, each of us, a little universe. Light takes time to reach us from distant places, and because of that, when we look into deep space, we look back in time. The farther away something is, the older the light we see. When you look at the Andromeda galaxy, you see it as it was 2.5 million years ago, when our ancestors had not yet learned to control fire. When you observe a galaxy 10 billion light years away, you see the universe as it existed when our solar system did not yet exist. Every astronomical image is a composite of different moments in cosmic history. A photograph of a galaxy cluster containing thousands of galaxies at different distances shows thousands of different moments in time simultaneously, with the nearest galaxies appearing as they were hundreds of millions of years ago, while the most distant appear as they were billions of years before that. Telescopes are time machines. The Hubble Space Telescope and the James Webb Space Telescope do not merely see far, but see early. When Webb images galaxies that existed just 300 million years after the Big Bang, it shows us the universe when it was only 2% of its current age. We are watching cosmic infancy. What makes recent discoveries even more remarkable is that some of what Webb has revealed challenges our theories. Galaxies in the early universe appear too large, too organized, too mature for their cosmic youth, like finding oak trees in a forest you thought was planted last spring. Either our models of galaxy formation need revision, or something unexpected happened in the early cosmos, which is precisely how science advances, with observation challenging assumption and data demanding new understanding. The cosmic microwave background, detected by Penzias and Wilson and mapped with extraordinary precision by satellites like WMAP and Planck, represents the farthest back in time we can directly observe using light. Before that 380,000 year mark, when atoms formed and the universe became transparent, there was no freely traveling light to see. The universe was plasma, opaque electromagnetic fog. Beyond that curtain, we cannot look using photons. Future experiments may detect primordial gravitational waves that could tell us about even earlier epochs, perhaps even the inflationary period that Guth proposed. But for now, the cosmic microwave background is our baby picture, showing the universe when it was 0.003% of its current age. Human intellectual history is a sequence of demotions from cosmic centrality. Earth was considered the center of everything for most of recorded history, with the sun, moon, planets, and stars revolving around us. Copernicus showed that Earth revolves around the sun, making us just another planet. We learned our sun is one of hundreds of billions of stars in the Milky Way, not special, but ordinary. We discovered the Milky Way is one of trillions of galaxies. And now we understand our observable universe is just a bubble of visibility in something potentially infinite. We went from being the center of everything to being cosmically unremarkable. By every metric except one, we figured it out. No other arrangement of matter in the observable universe has demonstrated the ability to determine its own cosmic address and read its own atomic autobiography. That capability is not insignificant. One way to grasp temporal scales is to compress the entire 13.8 billion year history into a single calendar year. a technique Carl Sagan popularized with his cosmic calendar. The Big Bang happens at midnight on January 1st. Every month represents roughly 1 billion years. Every day represents about 38 million years. Our Milky Way galaxy does not form until around March. Our solar system does not form until late August. Earth solidifies and life appears in September. For months, that life is nothing but single-celled organisms. The Cambrian explosion, when complex multicellular life suddenly diversified, does not occur until December 17th. Dinosaurs appear on December 25th and go extinct on December 30th. Their entire 165 million year reign lasting just 5 days on the cosmic calendar. All recorded human history happens in the final 14 seconds of December 31st. Every empire and revolution, every war and peace treaty, every work of art and scientific discovery. The scientific revolution began about 1 second ago. Your entire lifetime amounts to a fraction of a cosmic second. This context does not make you insignificant. You exist in the final moments of a grand cosmic story that has been unfolding for eons. And yet, in that cosmic second, you have developed the ability to understand the preceding 13.8 billion years. That is remarkable, not diminishing. What we do not understand remains as important as what we do. Ordinary matter, the stuff of stars and planets and people and everything we can see and touch, accounts for less than 5% of the total mass energy budget of the universe, according to Planck satellite measurements. About 27% is dark matter. Vera Rubin's observations of spiral galaxies in the 1970s showed that stars in the outer regions orbit their galactic centers far too fast to be held in by the gravity of visible matter alone. The galaxies should fly apart. Something else is there, invisible, providing gravitational glue. Subsequent observations of galaxy clusters, gravitational lensing, and the structure of the cosmic microwave background have confirmed that dark matter exists, but decades later we still do not know what it is. We can map its distribution, we can measure its effects, we cannot explain its nature. The remaining 68% is something even stranger, which we call dark energy for lack of any better understanding. In 1998, 2 independent teams of astronomers studying distant supernovae, led by Saul Perlmutter on one side and Brian Schmidt and Adam Rees on the other, made an astonishing discovery that earned them the Nobel Prize in Physics. The universe is not just expanding, but accelerating. The expansion rate increasing with time. The universe is running on borrowed energy. 68% of everything that determines cosmic destiny comes from the vacuum itself, a kind of pressure inherent in empty space that pushes the universe apart faster and faster. We have named our ignorance dark energy. The way ancient cartographers wrote here, be dragons on unexplored territories. We know it exists. We do not know what it is. What this cosmic accounting tells us is humbling. We have decoded the behavior of the universe with extraordinary precision. We can predict the cosmic microwave background's temperature fluctuations to 5 decimal places. But most of the universe is made of substances we cannot explain. That is where we stand, triumphant in technique, humbled by mystery. Dark energy will eventually push every galaxy beyond the Milky Way's local gravitationally bound group over our cosmic horizon. Future astronomers inheriting this accelerating expansion will see a universe that appears smaller and simpler than ours. They will look up at night to see only local stars, while everything else will have redshifted into undetectable oblivion. Unless they inherit exceptional records, they will not know that the universe once contained trillions of visible galaxies, or that those galaxies provided the evidence for expansion itself. They will be cosmologically impoverished compared to us. And the question that haunts me is whether we are similarly impoverished compared to observers who might have existed billions of years ago, whether cosmic Evidence that was once obvious has since vanished beyond our detection forever. The day our knowledge of the cosmos ceases to expand, we risk regressing to the parochial view that existence revolves around us. In that diminished world, territorial disputes and tribal grievances would seem proportionally larger. The cosmic perspective is not a luxury but a necessity for a species that holds the power to destroy itself. When you understand your place in the universe, when you grasp that every human who ever lived shares the same cosmic origin, the differences we fight over recede into proper proportion. We are all constituted from the same stellar forges. Every person you have loved and every person you have hated contains atoms manufactured in the same astrophysical processes. The stranger in a distant land breathes oxygen produced by the same cosmic mechanisms that gave you yours. The cosmic perspective does not erase our differences, but places them in context. Scale is where we started, and scale is the fundamental concept people miscalculate. When I say the observable universe spans 93 billion light years, that number needs anchoring. Light travels at about 186,000 miles per second, covering roughly 5.88 trillion miles in 1 year. That distance is 1 light year. The nearest star to our sun, Proxima Centauri, sits about 4.2 light years away. At our current fastest spacecraft speeds, it would take approximately 70,000 years to reach it, putting us back to an era when our ancestors shared the planet with Neanderthals. Our Milky Way galaxy spans about 100,000 light years across. Light requires 100,000 years to cross from one side to the other. The nearest large spiral galaxy, Andromeda, sits 2.5 million light years away. The nearest major galaxy cluster, Virgo, sits about 50 million light years distant. And the edge of our observable universe sits 46 billion light years away in every direction. Our galaxy has a diameter to thickness ratio of about 1,000 to 1, making it flatter than the flattest pancake ever made, with proportions better represented by a crepe or a tortilla than a disk. We live in a cosmic tortilla orbiting an ordinary star in an undistinguished region of space in the outskirts of the Laniakea supercluster, participating in a 230 million year orbit around the galactic center. Our solar system has completed that orbit about 20 times since it formed. Our sun was born in an unremarkable region of an unremarkable galaxy in an unremarkable part of the observable universe. The gas cloud from which it formed contains sufficient heavy elements manufactured in previous generations of stellar deaths, to create a system of planets, thousands of asteroids, and billions of comets. We are made of recycled cosmic material, at least second generation and probably third. The observable universe is vastly larger than the age of the universe times the speed of light, because space has been expanding the entire time light has been traveling, with cosmic inflation in the early universe, providing an additional dramatic expansion. The observable universe is just our cosmic bubble of visibility, while the actual universe is far larger and possibly infinite. Dark energy is accelerating the expansion, meaning our visible cosmos will shrink over time as distant objects recede beyond our ability to detect. Your physical scale relative to the cosmos says nothing about your significance. You are atoms forged in the hearts of dying stars, assembled into a configuration that became conscious, that became curious, that looked up at the night sky and determined where it all came from. You are the universe examining itself, asking questions about itself, searching for meaning within itself. That capability exists nowhere else we have yet detected. In 93 billion light years, we are not merely in the universe. The universe is in us. The cosmos had a beginning. The cosmos continues to evolve. Every atom in your body traces back to the Big Bang and to the thermonuclear furnaces within massive stars that exploded more than 5 billion years ago. We are not observers of the universe, but participants in it, born from it, constituted by it. We have been empowered by cosmic processes to comprehend cosmic processes. That is not smallness, but participation in something larger than any individual, larger than any species, larger than any planet or star or galaxy. When you truly grasp the scale of the universe, not just the numbers, but what they mean, you do not feel diminished. You feel like you belong to something so vast that the word vast loses its meaning. Within that immensity, somehow against all calculable odds, atoms arrange themselves into configurations capable of contemplating their own origins. We do not merely reside in the cosmos resides in us. And we have only just begun to understand it.